Okay, welcome back. So what we're doing now is we're starting to move our way towards this issue of life as defiance. And in the previous vignettes, what I've done is set up the what you could call the calculus of equilibrium, really just trying to implement the ideas of Gibbs in the paper that I showed you at the very beginning from the Connecticut Academy, Transactions of the Connecticut Academy of Sciences, in which Gibbs basically argued that we should think of equilibrium as entropy maximization. And now what we're going to do is we're going to generalize that a little bit. And what I mean by that is we're going to look at the case where we're a little bit out of equilibrium, and we're going to think about what are the forces that tend that system back towards equilibrium, and also how fast does that occur. So, so what you see here is the little cartoon that I already described in a previous vignette, and the point of that cartoon was just to argue in that case that the state of equilibrium is the entropy maximizer. That's the state here. It's a competition between the entropy of the left side and the right hand side. So that is to say that when one entropy, the left goes up, the right goes down, and vice versa. So that's intriguing. And as I'm going to try to repeat many times throughout the remainder of the course, this idea of competition is really central to the playing out of different processes. Sometimes we earlier in the term talked about surface volume competitions, and the case of the compartmentalization of an enzyme was a really interesting example of that, I think. And where we found that the surface terms were penalizing the substrate, they were enhancing the intermediate, because the bigger we made the volume, the harder it was for the intermediates to escape. And there was some balance point at which things were best. So here we have a competition. And now what I want to do is let's imagine that we start out with this configuration. So we already know what's going to happen. What's going to happen is that particles are going to flow from right to left, thus decreasing the entropy of the right-hand side, but increasing the entropy on the left side, and increasing the net entropy by traversing this curve right here, right? So we're going to move along that curve. And the thing I wanted to do is I wanted to give that a little bit of formal backdrop. This is not formal like formalism, but more just like trying to turn those words into equations. So I told you earlier that I could think of the total entropy as the sum of the entropy of the two subsystems. I'm using a single variable n to characterize the state of the system, because I know that the total number of particles is n total. The entropy is the sum of the left and the right hand sides. I know, because of the second law of thermodynamics, that in any spontaneous process, the entropy will tend to increase. And I can write this rate of change, or the differential of the entropy, in this form. Note this minus sign comes out here because of chain rule on taking the derivative of this guy with respect to n. So I have dsr by dn prime or something, by du. That's a bad variable. dsr by dm, and then dm by dn, where m is n tot minus n. So sorry, let me write that out. Yikes. So using m equals n tot minus n, and then dsr by dn I can rewrite as dsr by dm, dm by dn, and that's how I got this minus sign right up there. So that's what that's all about. So what I find is that at the end of the day, that I end up with a product. I have dn times this quantity, and I know that the entirety of that has to be positive. So somehow the system is going to move in a direction such that the total entropy increases, and that's going to be mediated by this driving force. The larger this quantity is, with either plus or minus sign, the claim I'm going to make is the more rapidly the system will return to equilibrium. So that's kind of the background. Now let's talk about actual implementation of this kind of thing. So there's a whole suite of laws, and I'm going to say law advisedly. They're really phenomenological descriptions of the observed properties of matter. That's really what this is. So I can pretend that I derived it somehow, and then actually I can do that using the binomial distribution. It's pretty fun. And if you want to see that, there's a paper um, that Ken Dill and I uh, and others, Gosh, wrote in American Journal of Physics a long time ago. I don't know when, but there's a little section that talks about how to get Fick's law out of the properties of the binomial distribution. But what's the point of this thing? It's just to remind you, I mean, we've already been through this, but it's just to remind you of the nature of the phenomenological law that we worked out. So we imagine we had two planes of molecules, and we imagined that the particles or the molecules in each of these two regions would flip coins, and everybody that got a heads would move one direction, everybody that got a tails would move the other direction. And what we said is, well, on average, n left divided by 2 are going to go in this direction, and n right divided by 2 are going to go in this direction if I'm flipping fair coins. And so the flux is going to be NL minus NR divided by 2 times some coefficient. It's basically saying that what we want to do, the larger the difference between the quantity on the two planes, the larger will be the mass transport. And so that is embodied in this schematic that I show you here, which plots the concentration as a function of position, but now treated as a continuous variable. And the point is that the flux in this case is greater than the flux in this case. And that is because the difference in the two planes is larger. And so all of this got codified, it all got sort of summarized phenomenologically in Fick's law, which tells us that there's a linear relationship between the flux, which remember has units of number per area per time when we're talking about molecular transport, and it's proportional to the gradient in the concentration with the coefficient that mediates those two things, the diffusion coefficient. So what I want to say now, and I think I have shown this already, I'm showing it now for a different reason. I'm showing it because now we're really going to look at what it says and think it through. So I'm claiming that there's a whole host of such laws. Why do I bring this up? Because we're talking about defiance. And my point is that if left to their own devices, systems will smooth out, they will equilibrate, they will homogenize. That's the kind of thing that I'm trying to drive at here. So let's look at this case. We've already talked about this. If I have a concentration gradient, if left to their own devices, the molecules will smooth out. I will end up with a homogeneous distribution. Here, the second case, I have a non-uniform temperature. And so in that case, if I now isolate the system and leave it to itself, what will happen is the temperature will smooth out until it's homogeneous. Here, if I stirred a system, and so there's somehow a difference in momentum across the stirred fluid, then there will be a flux of momentum. And once again, that will smooth out over time. It will homogenize. And so all of these are basically telling us the same thing, which is that the return to equilibrium, or the dynamics to equilibrium, and I'm going to say for small departures, where I'm not going to say what I mean by that, for small departures from equilibrium, that they will relax according to the dynamics that I just wrote, which is flux of whatever is equal to minus and then some transport coefficient, and then times the degree of disequilibrium. So that's the general format. Let's look at an alternative example to Fick's law. Let's talk about Fourier's law, which is really interesting and relevant. So this is the law of heat conduction. And what it says is that J of Q is equal to minus kappa times grad T. So this is the heat flux. It has units of joules per meter squared per second, for example. So it's energy per area per time. And then this thing over here has units of Kelvin per meter. So it's a gradient in temperature. It's telling me what's the change in number of the temperature as a function of how long I walk along the material. And so, by equating the two sides, that implies that the thermal conductivity, so this is called the thermal conductivity, it has units of joules per meter per second per degree Kelvin. So that's the units of the thermal conductivity. Let me just make sure that I did that right. So, yeah. Those are the units, and we could, in principle, write down an equation for the conservation of energy, and that would lead us to the heat equation, which I will probably have people look at in a homework. So, what's the summary of what I wanted to accomplish with this little vignette? Because it's basically setting the backdrop. It's saying that that systems, first of all, we've already said about compliance, about lack of defiance, that systems will go to a state of equilibrium. If you perturb them from that state of equilibrium, they will relax back to equilibrium, and the phenomenology that we often use to describe that return to equilibrium is these kinds of linear transport laws, where there's a simple linear relationship between the flux and the degree of disequilibrium. So it's that I wanted to pass along, because this is going to tell us about the dynamics of compliance, where the system would go if left to its own devices. And you're going to see, like, I'm going to make a calculation of what it takes to maintain the Bicoid gradient in the developing fly embryo. If I were to turn off the production of protein, for example, at the left or the anterior end, then the gradient would go away because of the degradation. If I were to turn off both the production and the degradation, it would still go away. The number of molecules would stay constant, but it would get smooth across the entire embryo. So the bottom line is that that one needs a drive to fight off these phenomenological effects, which are the fluxes that tend to bring a system to equilibrium. Okay, that's the message of that one.